Hello everyone and welcome back to another minute concept, this time about electric flux and Gauss's law. So what is electric flux? In the last few videos we discussed electric fields, Coulomb's law, and other intros to electrostatics. Now, this one is a bit of a step up. This topic describes how field moves or field behaves or field flows through any surface. And Gauss's law describes electric flux. So, in that sense, we need to first understand what is electric flux. So, imagine that we have a charge. Like we always do, let's always draw it first. So, we'll put like one small charge there and we'll make it positive. We know that the field of a positive charge always goes outward. And that's in any direction, that's radially outward. Now, imagine that we have ourselves a sheet of metal here. There. Or really any conducting material, or just any material in general. So, the field of this positive charge will pass through our surface. Right? So, we can imagine another arrow going in through here. It enters that way, and it comes out the other side. Oh. Comes out here. Now, the quote-unquote amount of charge, or amount of field rather, that passes through a surface here, that is what we call the flux. So this is flux. And it's actually in the dictionary as well, a similar definition, basically the flow of something. So this is the flow of field through any closed surface. And now, how about Gauss's law? What does that say? Now, imagine that instead of just having one sheet, we're going to encapsulate this this charge. And we're gonna make it a cube. It's not exactly the best looking cube, but just there. Okay, now imagine it is a cube, and it's going to have a charge inside. So there's going to be flux going out here, here, down here. So, Gauss's law states that the flux inside of any closed surface is going to be proportional to the closed charge. So basically, however many or however large the charge inside of the box or any container is, that's how much flux there's going to be. Or the flux is proportional to that. So let's say I double the charge of this positive charge, then I will double my flux. And that's regardless of the shape. So I can turn this into a ball, I can turn this into a pyramid, I can turn this into whatever, I can turn it into a blob, but it wouldn't change anything. And it would only depend on the amount of charge inside the surface. So enough about the drawings for now, we'll go about that later. We need to first understand what are the formulas for flux. So the electric flux formula itself, this right here, this one, not Gauss's law. Electric flux is given by, this is the symbol for flux. We have the electric field multiplied by the area of our surface multiplied to the angle, the normal. Now, this is the angle to the normal. And what does that mean? Okay, so let's go back and make another drawing. We said that we'd stop with the drawings, but right now we need another one. So this is just for visualization. And this is important for any problem solving involving flux. Consider this sheet again. Okay, so let's say that this charge is going to be emitting an electric field through here. We need to get the angle that the field passes through the normal line of this sheet. What is a normal line? Okay, a normal line is any line that is completely perpendicular to any other line. So, for example, I have here a horizontal line. My normal line would look like this. That's perpendicular. Now, what's my normal line to this line? My normal line to this line would be here. Or it can also be here. And then the same thing would continue. I can get the normal line for this line here. Go up. So go up as well. Basically, when you have a surface, all you have to do is find where a line that would be completely perpendicular would be facing. So in this case, our sheet is facing this way, so we can say that our normal line is here, right there. If our sheet were horizontal on the other hand, and let's say that we had our negative charge here, our normal line would be up here. So what do we want? We want to get the angle between the electric field line and our normal line. So I'll get rid of this other drawing first. Let's say that this line here, our electric field line, isn't actually going straight or perpendicular to the normal. Let's say that it was a bit angled. Let's say it was going this way. So if we continue going here, we can see that there's actually an angle forming between these two. And this is the angle that we're concerned about. Let's say that this is 30 degrees. This is the angle that we want. The angle away from the normal. We're not concerned with the angle to the surface, but instead our reference point is the normal line. So let's have a few exercises on determining the angle sheet problem. Now let's imagine that there's another charge here. This one will be positive again, just so that we can have our electric field lines pointing outward. And we'll signify our normal line with this vertical line right here. Oh, that's almost perfectly straight. Okay, there. This is our normal line. So I will draw the electric field lines, and maybe you guys can pause the video to see what the angle between the normal line and our electric field lines are. I'll be drawing 3 different lines. So here, this is 1, this is A. Then there's another one here going I'll make it go the other way. In this way. Don't mind that it's not straight, it's not a good drawing. And then there's also this way. Now keep in mind when solving this is B, this is C. The angle between here and here, I'll signify it. This is 60 degrees. Okay, so now keep in mind that on any surface, let's say this is another one, normal lines do not only stretch out from the middle. There are many normal lines. So as long as they're all perpendicular, that is a normal line. So in this case, you can imagine another normal line beside it, or in this case, another normal line. So you guys can pause the video and try to see if you can figure out the angles. Alright, so maybe if you guys have paused the video already, or maybe if you guys didn't, I mean, I don't really do that whenever I watch these type of videos, but the answers for these are the following. We can see that this line here, while not perfectly straight, is pointed straight up. Now, like I said earlier, there are multiple normal lines. And it's not just this purple one. Instead, this was just for reference. So we can say that there's actually another normal line right here, stretching out straight up. This is also 90 degrees. So the angle is 90 degrees. Or, actually, it's in perfect alignment to the normal line. So it actually doesn't have any angle. Now, how about this? So we know that the sum of the angles here is supposed to be equal to 90, right? And we know that the angle between our field line and the surface is 60. But what we want is the angle between our field line and the normal line. So seeing that it's supposed to be equal to 90, we'll just do 90 minus 60, and we'll be left with 30 degrees. So this angle here is 30 degrees. And here, this is another situation, and to be going straight up, that's one of our normal lines. So we can see that the angle between these two are perfectly perpendicular. So answer to letter C is 90 degrees. I'll get rid of every other angle here except for, oops, not me to do that. I'll get rid of the angles except for these two. Let's clear out the right thing. I'll get rid of this too. Done. There. Okay. So there are two cases here that maximize and minimize the flux through any surface. Whenever the field line is completely aligned with our normal line or any normal line are perfectly perpendicular to our surface, that means that the angle is going to be 0 degrees. And cosine 0 is equal to 1. That said, that means that the electric flux is always maximized whenever the angle between the electric field line and the normal line is 0. So basically, it's maximum when it's perpendicular. When perp. There. So basically, you just want to see always that it's going to be in like a T. There. So if that's the angle between our surface and our electric field line, then we maximize our flux, because that means that it's basically just going all through. Maximum field is going through. Now how about if it's parallel? Whenever it's parallel, that means that we have a 90-degree angle between the electric field line and the normal. That also means that we're not going through the surface. If this is our surface, from the front it would look like we're going this way. The electric field would be going that way, and this is our surface. They're not going to make contact, and so the field will not flow through any surface, right? And that said, that means that whenever cosine is equal to 90, or the angle is equal to 90 rather, we get a value of 0. So the flux is 0 when it's parallel. That works for two-dimensional surfaces or flat surfaces. And this could work also for any shape. I can make this a circle, I can make this a triangle, I can make it anything. As long as it's not encapsulating the charge, then that is the conditions for maximum and minimum. Now, hopefully that's clear. I know that one might be a bit confusing because normal lines are, well, they're really the backbone. That's why I had to keep reiterating them. Normally, that's where people make mistakes. So we want to make sure that we can avoid those careless mistakes. Right, so now, how about Gauss's law? Let's copy paste this. Oops. Okay. So we know a while ago that this is for two-dimensional surfaces. Now, how about if we had a three-dimensional surface? Oh, let's remove everything except for the charge. Now, what is the simplest three-dimensional surface other than a cube? Well, even a cube in and of itself is actually already quite complicated. It has 1, 2, 3, 4. It has 6 faces, right? It has 6 faces, and that's a lot. So, what is another really simple three-dimensional object? Another really simple three-dimensional object is a ball or a sphere. Quite literally the simplest because it has no sides, and it's perfectly symmetrical. Now, Gauss's law says that whatever the flux inside of whatever the charge is inside, or the magnitude of the charge is inside, that is going to be proportional to the amount of flux that goes through that surface. Now, Gauss's law uses a constant called the constant of free permittivity. The free permittivity constant. So this is equal to Q. This is Gauss's law. Gauss's law is equal to Q over epsilon naught, wherein epsilon naught, or the constant of free permittivity constant, is equal to 8.85 times 10 to the power of negative 12. And this is Coulomb per Newton meter squared. There's actually, just for some extra added knowledge here, epsilon naught is actually used to get our favorite constant so far, Coulomb's constant. Coulomb's constant is given with the formula, hold on. Coulomb's constant is equal to 1 over 4 pi epsilon naught. And if you recall, K is used in getting the electric field. So why don't we try to rewrite this formula with this knowledge? So we'll just turn this into flux. Okay, so this is K, right? And we know that E is equal to k times q over r squared. So all we have to do now is just write our q over r squared. So times q r squared and the area. Now what's the surface area of a sphere? The surface area of a sphere is 4 pi r squared. And we can see from here that these cancel out, get rid of each other, and we're left with q over epsilon naught. And there you have it. That is it. And this is not only for a sphere. This actually works for all of them. And all three-dimensional shapes, regardless of their form. And that is given by Gauss's law. So that's just some added knowledge for you. Now let's try applying this knowledge, right? Let's say that we have this ball and we want to get the total flux going through it. Now we know that it's going to be equal to the total charge inside over epsilon naught. So all we have to do is figure out the charge inside. What if I give this charge a magnitude of 8.85 times 10 to the power of negative 6, or basically 8.85 microcoulombs. So that's 8.85 times 10 to the power of negative 6. So I'll just put that over our permittivity constant, which is 8.85 times 10 to the power of negative 12. These will cancel out. And we'll be left with a flux of 1 times 10 to the power of negative 6 minus negative 12. That would just turn into addition. So we'd be left with 1 times 10 to the power of 6, or simply 10 to the power of 6. And the what's it called? The unit for this is Newton meter squared per coulomb. So that's pretty much how you use it. And now we can try problem solving. Oh wait, actually before we move to problem solving, there's also another key point that I want to emphasize about Gauss's law. Like I mentioned earlier, it only works when it encloses a charge. Now what happens if I put this charge outside? The charge outside would be sending electric field in, and then it would go through, and eventually it would go back out. So what is the total flux? What came in went out. So that's basically a plus, then you add a minus, and that amounts to 0. So if there is no charge enclosed inside the surface, then the flux is equal to 0. And now how also do we describe flux when we're talking about direction? An inward flux, if we make this negative, for example, if we make this negative, then it would be negative flux. Flux is scalar, by the way, but we put negative just to determine the direction. Or not exactly direction, but the behavior. So this would be negative flux. Now how about if it were the other way around? If we make it a positive charge, then it would be going outward, and we'd be getting a positive flux. And that's it. So that's pretty much the basics of electric flux. So now let's try problem solving. So first, we have to read the question and understand it. So let's go. You measure an electric field of 1.25. Oops, this is supposed to be to the power of 6 there. 1.25 times 10 to the power of 6 newtons per coulomb at a distance of 0.150 meters from a point charge. There is no other source of electric field in the region other than this point charge. What is the electric field to the surface of a sphere that has this charge at its center and that has radius 0.150 meters, and what is the magnitude of this charge? Alright, so here, what do we do first in any problem? We have to list down the given. So we know that our given here is, let's use another color. Let's use we know that our electric field is 1.25 times 10 to the power of 6 newtons per coulomb. And we know that the distance from our point charge or our source of the electric field is 0.150. Now, there is no other source of electric field, so that means that this is our only charge. The charge that we have emitting this field is the only charge. So how do we get the electric flux going through the surface of the sphere that has the charge at its center? Now, we just have to analyze the area of a sphere. What is the surface area of a sphere equal to? The surface area of a sphere is equal to 4 pi r squared. Alright, so now we know what the area is, right? And we know that the equation for flux is the electric field times the area times the angle between these two. Now, they're not exactly at an angle. It's not stated here. So we can just disregard this and assume that it's maximized. So we're left with just E8. So we can plug in our values and we can solve from here. So we're going to take 1.25 times 10 to the power of 6 times 4 pi 0.15. Oops, let's move this a bit. Let's shrink it. Where did this guy go? Where did this come from? Well, anyway, 0.15, and it's going to be squared. So all we have to do now is multiply. We can put it into our calculator and we'll get, hold on, let me get mine. So 1.25 times 10 to the power of 6 multiplied by 4 pi times 0.15 squared. And that gives us an answer of 3.53 times 10 to the power of 1, 2, 3, 4, 5, 10 to the power of 5. Now, what's our unit? Our unit again for flux is Newton meter squared per coulomb. And that's it. That's how you get the flux. And now, how do we get the magnitude of the charge? Okay, so now we have this, right? We want to get the magnitude of the charge. What formula for flux allows us to know or involves the charge? That's when we use Gauss's law. If we recall, Gauss's law says that the flux is equal to the charge over epsilon naught. And actually, it's really easy to get the charge now because epsilon naught is a constant. And we already have the flux. So basically what we're saying is this is equal to 3.53 times 10 to the power of 5. Now, if we want Q, what do we have to do? All we have to do is multiply our constant to our flux. So Q is going to be equal to 3.53 times 10 to the power of 5. And this will be multiplied to 8.85 times 10 to the power of negative 12. So now let's multiply. So 3.53 times 10 to the power of 5 multiplied to 8.85 times 10 to the power of negative 12. And we're going to get an answer of 3.12 times 10 to the power of negative 6 coulombs. Or basically 3.12 3 microcoulombs rather, 3.12 microcoulombs. So that is how you solve for this question. If you want the formula breakdown, basically what we did was we just used this formula here, and for the next part we just took hold on, let's move it here. The flux is equal to Q over epsilon naught, and this is also equal to EA. Since we know what this is, we can just remove this side and we're going to multiply epsilon naught to our flux. That's how we get our charge. So I hope that made sense. If you need to redo it, feel free to replay the problem so that you guys can get it. But that's basically it. And yeah, so now let's try another question. A thin hollow sphere of radius 0.250 meters has an unknown charge distributed uniformly over its surface. At a distance of 0.300 meters from the center of the sphere, the electric field points radially inward and has a magnitude of 1.80 times 10 to the power of 2. This should be another typo there. Times 10 to the power of 2 newtons per coulomb. How much charge is there on the sphere? Alright, so it seems like we're going to go back to this process of thinking. First, we have to draw. How do we draw this problem? We have to analyze it closely. So we have a thin-walled hollow sphere. So we have one sphere first. Let's draw that sphere. We have one small sphere, and the radius of this sphere, let's make it bigger. The radius of the sphere is 0.250 meters. Now we also have a distance of 0.300 meters from the center of the sphere being involved. So we have another like quote-unquote layer where all of this is a total of 0.300 meters away from the center. We want to know the charge on the sphere. So what do we do first? First, all we have to do is, well, get the flux, because we can only get the charge once we know the flux, and the flux isn't given. So how do we get the flux here? First, let's list down the given. So again, we'll go with here. Our electric field is equal to 1.80 times 10 to the power of 2 newtons per coulomb. And we also have our distance. Our distance that we're concerned with here isn't 0.250, but instead it's 0.300. Simply because we're trying to see we're trying to get the flux in reference to the distance from the center of the sphere. And that's also because we have the magnitude at that point. Right? And yeah, so that's where we have to start. Excuse me. The flux also doesn't change. Remember that. The flux doesn't change with the dimensions of our shape. Like I said earlier, regardless of shape, the flux will stay the same. What matters is how much charge there is inside. So, taking the electric field at 0.300 compared to 0.250, which we don't have the field at 0.250, it actually doesn't make any difference. It will still be the same. So our R is 0.300 meters. Now, how do we get the flux? Again, we just go use our formula. So, we'll use our electric flux, which is equal to EA. And we don't have a cosine theta here because it seems to be flat. Or actually, if you just tilt it anywhere, any distance of 300 meters would essentially be flat. So now, all we have to do is we have to plug in our values and we'll get the answer. So for our flux, all we have to do is just put in our values. We have 1.8 times 10 to the power of 2 times our surface area for a sphere, which we got earlier, 0.3 squared. And this will get us an answer of, hold on, 0.8 times 10 to the power of 2 times 4 times pi times 0.3 squared. That gets us 2.03 times 10 to the power of 2. And this is Newton meters squared per coulomb. So that's it. That's our flux. Now, what do we do from here? How do we get the charge on the sphere? We just go back to what we did a while ago. So we know that the flux is equal to Q over epsilon naught. So if we want to get Q, all we have to do is leave it alone. So we're going to multiply epsilon naught to both sides, and we'll get Q is equal to our flux times epsilon naught. So we can just plug in our values. We'll have 2.03 times 10 to the power of 2 multiplied to our epsilon naught, which is 8.85 times 10 to the power of negative 12. And there. Now we have our answer, which should be... Hold on, let me try. Let me see if I have enough digits on my calculator for this. I do not, but I have the answer. It's supposed to be 1.8 times 10 to the power of negative 9 coulombs. This is nanocoulombs. So negative 9 is nano. I don't have enough digits on my calculator, so on your end, it might just look like this. It might just be 0.000000001. Don't worry. I mean, basically the same thing at that point. You can just attribute that to the calculator model. I don't know if there's any other way for me to get more digits, but yeah. If you got 1.8, good job. If you got 1.0, also good job. So that's it. Now, on to the next question. So this one's a bit more interesting. It's about the Earth. So the Earth is a conductor and has a net electric charge. We know this because we have a magnetic field. So the resulting electric field near the surface of the Earth has an average value of about 150 newtons per coulomb, and this is directed towards the center of our planet. And what is the corresponding surface charge density, and what is the total surface charge of the Earth? This is with the radius of the Earth being 6.37 times 10, this is not 106, times 10 to the power of 6 meters. So there we have it. That's our question. First what we can do is we can just draw the Earth, make it blue because our planet is blue. There. So we can see here, based on the given, that we have an average value, or the electric field near the surface is about 150 newtons per coulomb. Now, what does that mean? Basically, we can say that we're describing the electric field on the surface, right? And our radius here is 6.37 times 10 to the power of 6 meters. And there, so that's our given right now. And the electric field is 150 newtons per coulomb. So first, what is the corresponding surface charge density, and what is the total surface charge of the Earth? Alright, so this is a two-parter. So first, what we can do here is try to identify the flux. So we use Gauss's law again, but maybe this time we can take a bit of a shortcut. So take a look here. We have Gauss's law equal to we have Gauss's law being equal to Q times epsilon naught, and we also have the other equivalent of electric flux being A cos, or let's just remove that, so EA. We have the electric field, we can get the area, and we need the surface charge density, and we also need the surface charge. So what do we have to do? All we have to do is we can shortcut it. We can just remove this guy in the middle because they're all equivalent anyway, and we'll move this together. Basically, to get Q, it would be equal to E times A times epsilon naught. And multiplying our given together should get us our total surface charge. So let's try using this shortcut, and we should get the right answer. So I'll use another pen. Hold on. So our given, we have the electric field at 150 newtons per coulomb times 6.37. Well, the surface area is not just 6.37, so we'll have 4 pi. That's not a nice pi. 4 pi 6.37 times 10 to the power of 6 squared, and then multiplied. That's not enough space. Okay, maybe that would work. Multiplied by epsilon naught, which is 8.85 times 10 to the power of negative 12. So putting this all together would give us our Q. So let's try it. Let's multiply all of them together. So we'll have 150 times 4 times pi times 6.37 times 10 to the power of 6 all squared multiplied by 8.85 times 10 to the power of negative 12. That is a long computation. So there it is. So we should have an approximate charge of 6.77 times 10 to the power of 5 coulombs. There. So there you have it. That's our surface charge, and that answers letter B. Now we can actually designate a sign here. We didn't designate a sign a while ago, but this is just for practice. We can designate a sign here by determining the behavior of the field. It says here that it's going inward, and we know that inward fields are a behavior of negative charges. So we can say that this is a negative charge. Now, anyway, so we want the surface charge density now. And we know our Q. Surface charge density is given by small sigma. So this symbol. That is not good. Basically a sideways 6. There. That's not the best way to draw it, but it's basically it. So the enclosed charge over the area. This is similar to just our standard density, which is equal to I can't recall the Greek letter, so we'll just use D for now. The density is equal to mass over volume. Basically the same thing. The amount of charge per area. The amount of mass per cubic meter. And ours here is per square meter. So all we have to do is just plug in our values. 6.77 times 10 to the power of 5 coulombs all over our area, which is 4 pi, that really long number from a while ago. What is that? 6.37 times 10 to the power of 6 times 6.37 times 10 to the power of 6 squared. And this should get us a surface charge density, which is, hold on, 10 to the power of 5 over 4 pi times 6.37 times 10 to the power of 6 all squared. And that should get us another really small number. I can't get it to appear on my calculator, but it's supposed to be negative 1.33 times 10 to the power of negative 9 coulombs per meter squared. And that is our surface charge density. If you don't have enough space on your calculator for whatever reason, just like mine, you might just see negative 1.0 times 10 to the power of negative 9. That's also correct. So if you got 1, good job. If you got 1.33, also good job. And that's basically it. That wraps it up for Gauss's law and electric flux. This is a bit of a long video, and I hope you understand why. You can't understand Gauss's law without electric flux, and you can't understand electric flux without Gauss's law. And these two go hand in hand because they pretty much explain how electric fields behave in terms of actual space. And when we have, for example, a container that we can say quote unquote insulates an electric field or an electric current, we need to make sure that we understand the flux that's actually going through that object. So when you buy something that says, for example, it's an insulating material or it's rubber, you can maybe imagine how electric flux plays into that, because it wouldn't allow, or it restricts the flow of electricity, and consequentially possibly even the electric field of whatever appliance or source of electricity that is. So I hope you guys can appreciate the hand-in-handness of these two topics. And of course, I hope you guys learned something from this video, and yeah, I'll see you guys in the next few topics, which is more about electrodynamics, particularly electric potential, and after that we're going to move on to alternating and direct currents, as well as resistors and our favorite Ohm's law and Kirchhoff's rules. And yeah, so that's it. Thank you everyone, and I hope you guys learned something. I'll see you all in the next video. Goodbye.